4 light-years away, something huge is moving through the dark, and we almost missed it. It is not a strange galaxy at the edge of the observable universe. It is not an exotic object in some distant cluster. It is a world right next door, orbiting the nearest stars to our own sun, hiding in plain sight for generations. At almost the same moment, a much smaller visitor slipped through our defences closer to home, a chunk of rock that could erase a city, and arrived with far less warning than anyone is comfortable with. Together, they reveal an uncomfortable pattern. The universe can keep enormous secrets, even when they are practically on our doorstep. And tonight, we are going to go looking for them, and test how much we really know about the space around us. If you step outside on a clear night and look toward the southern sky, you cannot see Alpha Centauri with the naked eye from most of the northern hemisphere. If you could, it would appear as a single bright point, just another star in a crowded sky. In reality, it is our closest stellar neighbour, a complex family of stars only about 4.3 light-years away. 2 of those stars, Alpha Centauri A and B, are sun-like and locked in an 80-year dance, orbiting each other in slow, graceful loops. A third, much smaller red dwarf called Proxima Centauri circles farther out. For a long time, we treated that system mostly as a backdrop for science fiction. Then we pointed serious instruments at it, and something strange happened. Precision measurements showed one of the larger stars wobbling ever so slightly. The motion was so small that it looked like noise at first, just tiny shifts in the star's spectrum. But as the data accumulated, a pattern emerged. Something was tugging on that star. The best explanation was not a companion star. It was a planet, a gas giant roughly similar in mass to Saturn, orbiting at a distance where temperatures could allow liquid water to exist on moons. The planet itself would be a world of deep clouds and crushing pressures, not a place for oceans and forests. But large moons around such a giant could in principle host all the ingredients of habitability. For many people, this immediately brought to mind the fictional moon Pandora from the film Avatar and other imagined forest worlds that circle giant planets. Scientists, to their credit, were more cautious. Detecting a planet by the wobble it causes is not the same as seeing it directly. Still, the idea that our nearest neighbouring stars might host a Saturn-like world in a potentially temperate zone was electrifying. It meant that if advanced life ever developed there, its night sky would be dominated by 2 suns, and the view from its moons would be unlike anything on Earth. It also meant that we might, one day, be able to see that world with our own eyes through space telescopes. Then, just as quickly as it appeared, it vanished. Follow-up observations were made. The wobble seemed to fade. Schedules were shuffled, data were reanalyzed, and astronomers went back to the system again. Nothing. The signal that looked like a gas giant near Alpha Centauri simply was not there anymore. For a time, the most boring explanation was on the table. The planet had never existed. The detection had been a statistical fluke, a ghost conjured by imperfect measurements and hopeful minds. That is the kind of conclusion scientists hate to reach, but are trained to accept. Rather than give up, though, teams all over the world began to ask a different question. If the planet really is there, how could it hide from us? They ran millions of orbital models, changing the tilt, the eccentricity, the timing of the planet's path around its star. That is when a more unsettling picture emerged. The orbit that best fit all the data was not a neat circle like the one Earth follows. It was stretched, elongated, a cosmic oval that carried the planet from near the inner system to the colder outer regions over the course of many years. The world had not disappeared. It had simply moved to a part of its orbit where our instruments could no longer pick up its subtle gravitational fingerprint. This was both reassuring and disturbing. Reassuring because it suggested the original discovery was not a mistake. Disturbing because it meant we are only glimpsing this world during a small fraction of its long journey. For the rest of the time, it may be too far from its star, too cold, or simply aligned in such a way that our telescopes fail to register its presence. And remember, this is all happening in a system right next to ours, in a place that has been the focus of intense attention for decades. If we can almost miss a Saturn-sized planet there, what else are we not seeing farther out? Things get even more precarious when you remember that Alpha Centauri is not a simple system with a single star and a single planet silently orbiting. It is a gravitational circus. The two big stars revolve around each other every 80 years, their separation constantly changing. The third, tiny Proxima, lurks far away on a likely elongated path of its own. That means any planet trying to hold an orbit in the region where liquid water could exist has to thread a narrow needle. Gravitational pulls from all three stars could, in principle, destabilize its path over long timescales, slinging it inward or outward, and dooming any long-term climate stability. Computer simulations suggest it is barely possible for such a planet to survive for billions of years. The stable orbits that work are narrow bands in a sea of chaos, like a marble balanced in a shallow groove on a vibrating plate. One wrong bump, and the system changes forever. If that Saturn-like planet exists, it has spent eons walking that tightrope. Its moons, if any exist, would have watched their skies slowly shift as the companion stars of Alpha Centauri traced out their own grand orbits. Now we stand here with our first hints, trying to reconstruct the story from a few years of limited data. To do better, we need more than wobbles. We need to actually see the planet. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, is designed with a powerful coronagraph, a device that can block out the blinding light of a star and reveal the faint glow of planets around it. Roman will be able to survey nearby systems with a sensitivity and contrast beyond anything we have today. Alpha Centauri, with its proximity and intriguing hints, is a prime target. There is a real possibility that Roman, perhaps in combination with other instruments, could give us the first direct image of this hidden neighbour. Imagine what that would feel like. To watch a picture come in of a pale, banded world, maybe with a thin ring system hanging in the blended light of two suns. To analyse the colours of its reflected light and infer the composition of its clouds. To see changes over time that hint at weather on a world 4 light-years away. Just thinking about it pulls you forward, invites you to follow the chain of discovery. And yet, while we dream of photographing distant planets, something else reminds us that we have serious problems much closer to home. In late 2024, surveys scanning the sky for moving objects flagged a new point of light. At first it looked like thousands of others, a faint speck drifting slowly against the background stars. But when its path was calculated, the numbers did not look routine. This object, a small asteroid, was on a trajectory that brought it into Earth's neighbourhood. Follow-up measurements refined its orbit and narrowed the uncertainties. The more data went in, the more uncomfortable the picture became. There was a non-trivial chance that this rock would not just pass by, it might actually hit. The object was estimated to be somewhere between about 130 and 300 feet across. That does not sound impressive compared to the great mountain-sized asteroids we see in disaster movies. It is closer in size to a city block or a 15-story building turned to stone. But if such a rock entered Earth's atmosphere at typical asteroid speeds, the energy released would rival several large nuclear weapons. It would not trigger a global extinction event. It would, however, flatten everything for miles around the impact point and send shockwaves ripping across a wide region. The early calculations suggested that the chance of impact was on the order of a few percent. In everyday life, a few percent chance might be acceptable. You might take a route that has a small chance of traffic. You might tolerate a slight risk of rain on a walk. In planetary defence, a few percent means something else entirely. It means that if you repeated history 100 times with slightly different initial conditions, that rock slams into Earth in several of those timelines. You do not want to leave that possibility unexamined when the potential cost is a devastated city and thousands or even hundreds of thousands of lives. NASA has developed careful guidelines to decide when to escalate an asteroid threat. Most rocks discovered so far are either very small or clearly on safe paths. This one sat uncomfortably in the middle, small enough to have been detected late, large enough to do severe damage. And the timing was bad. Its closest approach was not decades away, it was soon. Within weeks, this one object had the attention of multiple space agencies, observatories, and modelling teams. There was only one way to cut through the uncertainty. Someone had to measure the asteroid more precisely.
That is where the James Webb Space Telescope entered the story in a surprising way. Webb orbits far from Earth and spends its days studying the faint light of distant galaxies, exoplanet atmospheres, and newborn stars. Its observing time is precious, planned out years in advance. Changing that schedule is a serious decision. Yet in this case, NASA and its partners chose to redirect Webb's attention to a tumbling rock that was practically in our backyard. That choice alone tells you how seriously they take the threat of even a modest near-Earth object.
From a distance, an asteroid's brightness depends on two main factors. One is its size, the other is how reflective its surface is. A small, shiny object can look almost identical to a larger, dark one. If you only measure visible light, you end up with a range of possible sizes rather than a precise answer. Webb sees in the infrared the heat glow that objects emit. By measuring both reflected sunlight and thermal emission, scientists can solve for both reflectivity and size. In simple terms, they can tell the difference between a bright pebble and a dark boulder. In early 2025, Webb turned its segmented golden mirrors toward the asteroid.
Over multiple observations, it tracked the changing brightness as the object rotated, mapping out how its surface properties changed with angle. The data showed that this was not a bright, icy chunk, but a relatively dark rock. Using that information, researchers refined their models and converged on a new size estimate. The asteroid was roughly 160 feet wide, large enough to destroy a city if it struck, small enough that Earth's gravity and atmosphere would likely break it up before any global effects could occur. As the orbit calculations were updated with the new measurements, the probability of impact dropped. The rock would pass close by, but it would not hit us. Headlines celebrated the near miss. Scientists breathed easier.
It would be tempting to treat the whole episode as an overreaction, a dramatic scare that ended with a shrug of relief. But that is not how the people who work in planetary defense see it. For them, this was a wake-up call and a reminder of how thin our margin of safety really is. One of the most troubling details is how late we found it. An object capable of obliterating a metropolitan area slipped through our surveys until only a short time before its close approach. Part of that is due to the limitations of ground-based telescopes, which cannot scan near the bright glare of the sun. Many dangerous objects approach from sunward directions, where traditional surveys are effectively blind. Part of it is the sheer number of small asteroids in near-Earth space. There are millions of them, most uncharted, each with its own slow, patient orbit that occasionally crosses ours. We like to imagine that our catalogues are nearly complete, that every big rock is neatly logged in a database with a calculated trajectory and a safety label. The truth is far messier. Every year, new objects are discovered that pass closer than the Moon. Every year, we add more entries to the list of potentially hazardous asteroids. The episode with this one rock showed that even when we do notice a threat, we may have only months or years, not decades, to respond. It also showed that we are willing to divert our most advanced observatories to deal with the problem when necessary. Taken together, the hidden gas giant near Alpha Centauri and the nearly missed city killer in our own neighbourhood underline the same lesson. Space is full of things we do not see, even when they are very close. Some are vast worlds tracing complicated paths around nearby stars. Others are small stones on intersecting orbits with our own planet. We rely on subtle clues, tiny wobbles in starlight and faint moving points in survey images to infer their existence. With every new discovery, we are forced to admit that our picture of the universe, especially the part of it nearest to us, is still full of holes. The next time you look up at the night sky, it is worth holding two thoughts in your mind at once.
Somewhere in the darkness, a giant planet may be passing through a patch of space that our instruments cannot yet probe, carrying potential moons through alien seasons under twin suns. At the same time, small cold rocks are gliding silently along their orbits, some of them destined to pass close by Earth, and perhaps one day collide with it. The tools we're building now are beginning to reveal both kinds of hidden neighbours. As we push them harder and stretch them further, the question is not just what distant wonders we will uncover, but what other surprises might be waiting much closer than we think? To understand how fragile worlds can be, we need to look not just at what we almost missed nearby, but at what is most common in the galaxy as a whole. Our Sun is a fairly large star by local standards. Most stars are far smaller and dimmer. They are called red dwarfs, and they burn so slowly that they can shine for trillions of years. If the universe is a long-running play, red dwarfs are the main cast. It is natural to ask whether they host most of the life-bearing planets as well. For a long time, that idea felt almost obvious. If red dwarfs are the most numerous stars, then planets around them should be common. Because these stars are cooler and dimmer than the Sun, their habitable zones sit much closer in. A planet would have to orbit near its star to receive enough light and warmth to maintain liquid water on its surface. That makes these planets easier to find with current techniques. They tug more strongly on their stars and block more light during transits. Many early exoplanet surveys leaned into this advantage. One of the most famous discoveries was a compact system around a tiny star called TRAPPIST-1. At first glance, it looked like a dream come true. 7 planets, all roughly the size of Earth, packed into a system so tight that several of them could fit within the orbit of Mercury. 3 of those worlds appeared to sit in the region where a planet with the right atmosphere and surface conditions could support liquid water. Headlines called it a miniature solar system. Artists drew oceans under rust-red skies. It seemed like a nearby test case for life, on worlds that were familiar in size but orbiting a very different kind of star.
The reality turned out to be harsher. When the James Webb Space Telescope, often called Webb, began turning its infrared eye toward TRAPPIST-1, it was not just looking for silhouettes of planets, it was looking for air. When a planet passes in front of its star, starlight filters through any atmosphere it has. Molecules absorb specific colours. By measuring how the spectrum changes during a transit, astronomers can infer whether a world is wrapped in gas or bare rock. This is one of Webb's superpowers. On some of the TRAPPIST-1 planets, the verdict came back quickly. There was no sign of a thick, puffy hydrogen atmosphere like those that wrap small versions of Neptune. That was expected. But as the data accumulated, something more troubling appeared. For at least one of the inner planets, Webb found no evidence of a substantial atmosphere at all. The signal was flat where there should have been telltale bumps and dips. If any air hugs that surface, it is thin and carefully tucked away, not a generous ocean of gas like Earth's sky. Why would a planet in the right temperature zone lose its air? The answer lies in the star itself. Red dwarfs may be small, but they are restless. Many of them flare violently, spewing charged particles and intense radiation. Because habitable zone planets are so close in, they sit almost pressed against the furnace. Over billions of years, this constant assault can strip away an atmosphere, molecule by molecule, especially if the planet's magnetic field is weak or its gravity is modest. A world that starts out wrapped in a comfortable blanket of gas can be eroded down to bare stone. TRAPPIST-1 is not a fluke. Other red dwarf systems show similar behaviour. We see planets that should be in the right place on paper, but show signs of being scorched and dried out by their stars. Some may still have thin atmospheres of heavier molecules. Some may hold on to water deep underground. But the straightforward picture of a dozen temperate Earth twins around every small star has faded. Instead, we are left with a more complicated and uncomfortable thought. It is not enough for a planet to sit in the right zone. The star has to be kind. As you picture these worlds, it helps to imagine standing on one of them.
The star above would loom large in the sky, a dull red disk instead of a small white point. Days might last longer than our weeks, because many close-in planets are tidally locked, with one side always facing the star and the other trapped in eternal night. The sky would flare without warning as the star spits out radiation. If there was ever a thick atmosphere, it would be battered constantly, slowly pushed aside. You can feel how fragile the balance is, how easy it would be to tip from ocean covered to airless. Now, if you were designing a universe where life could thrive everywhere, you might expect some of these challenges to be compensated by other advantages. Perhaps many planets keep strong magnetic fields. Perhaps they replenish their air through volcanic outgassing.
Perhaps some evolve clever climate systems that move heat from dayside to nightside and hide water in protected basins. These possibilities are all on the table. Webb and other telescopes are hunting for them, but the early results hint at a darker conclusion. It may be much easier to strip away an atmosphere than to build one up in the first place. That becomes clearer when we look at the most extreme examples of planetary environments. Some worlds push the physics of climate and geology almost to breaking. One of the strangest does not even orbit a normal star. It circles a dead stellar remnant, a pulsar, a city-sized sphere of crushed matter spinning hundreds of times each second and blasting beams of radiation into space. The planet itself is stretched by gravity into a distorted shape more like a lemon than a sphere. Its days and nights are dominated by a relentless drizzle of high-energy particles. Observations suggest that such a planet could be cloaked in an atmosphere thick with carbon soot. The constant bombardment from the pulsar breaks apart molecules and drives strange chemistry in the upper air. Deep below, the immense pressures may have transformed much of its carbon into diamond. Imagine an entire world with layers of diamond mountain ranges buried under black clouds and lightning-lit haze. Whatever familiar meaning the word habitability has for us does not apply there. Yet it still obeys the same basic rules of gravity, radiation, and chemistry that shape every other planet. Another extreme case is a planet called TOI 561b. It orbits so close to its star that its surface is likely an ocean of molten rock. Temperatures there would turn any familiar material into vapor. If you could hover safely above it, you might see rivers and waves of glowing magma, with a faint atmosphere made not of nitrogen and oxygen, but of vaporized stone. It is a world that looks like a snapshot from the dawn of planetary formation, when young planets are still cooling from the heat of their birth. What makes TOI 561b interesting is not just how hostile it is the way its molten surface may be rebuilding its atmosphere. Volcanic activity and magma oceans can release gases trapped in a planet's interior. Carbon dioxide, water vapor, and other volatiles bubble out and form a temporary sky. In extreme cases, that sky can be stripped away again by stellar radiation, only to be rebuilt by more outgassing. The planet becomes a kind of breathing stone, exhaling and losing its air in cycles. Once again, the lesson is that building an atmosphere is possible, but holding on to one is the hard part. When you put all of this together, a pattern emerges. Red dwarfs offer long lifetimes, but they bathe their planets in flares and winds that can erode entire skies. Pulsar planets and ultra-hot lava worlds show how far matter can be pushed and still count as a planet at all. In between these extremes, each world negotiates its own fragile truce between gravity pulling gas down, heat trying to drive it away, and stellar tantrums adding random punches. Some planets will lose that fight quickly. Some will hang on for billions of years. A few may hit the sweet spot, where air is thick enough, stable enough, and gentle enough for complex chemistry to flourish on their surfaces. This is where your intuition about habitable zones can become a trap. It is tempting to look at a diagram with a star in the middle and a green band around it, and imagine that any planet inside that band is a potential Earth. What Webb and its companions are telling us is that the real situation is more like a maze. The green band is laced with dead ends, collapsing floors, and hidden doors.
You can be in the right place and still find yourself on a rock with no air. Or you can be slightly outside the classic zone, but equipped with an atmosphere thick enough to trap heat and keep oceans from freezing solid. You can feel the stakes of this when you think about the odds. If many stars strip the air from their inner worlds, then the number of planets with long-lived, stable atmospheres drops. Each new observation that reveals a bare rock where we hoped for a cloud deck nudges our estimate downward. Perhaps life is resourceful and can cling to underground reservoirs or deep ocean vents. Perhaps there are biospheres that never see the light of their star. Even so, complex surface ecosystems like the ones we know on Earth may be far more rare than we once imagined.
As you follow this trail, you might find yourself asking a simple question. Are we unlucky or lucky? Are we discovering that many of the nearby worlds are hostile only because our tools are tuned to find the easy targets first? Or are we catching a glimpse of a deeper truth, that stable blue worlds with thick skies and quiet yellow stars are the exception rather than the rule? Webb cannot answer that alone, but every new spectrum and light curve is a clue placed on the table in front of us. For now, red dwarfs remain both promising and dangerous. Their long lifetimes mean that any world that manages to keep its atmosphere could enjoy a stable environment for timescales far longer than Earth has existed. Their activity means that achieving that stability is a heroic feat of planetary engineering carried out by gravity, magnetism, and chemistry without conscious design. Somewhere out there, a few planets may have pulled it off. When you hear about each new discovery, each possible Earth-size world in a habitable zone, it is worth pausing to ask not just where it sits, but what its star does to it day after day. If you were to sketch a map of the galaxy, with each star colour-coded by how kind it is likely to be to its planets, you might find large swathes painted in harsh shades. Flaring dwarfs, pulsing remnants, hot young stars that blast away air before it can settle. Threaded through that map would be narrower bands of gentler light, stars that spin slowly, stars with calm magnetic fields, stars like our Sun. The worlds that orbit them, with the right mass, the right rotation, the right internal chemistry, and the right history, will be the rare jewels in that sea. We are only just beginning to see those jewels directly. In a few cases, Webb has already detected water vapour in the atmospheres of small planets, though most of those lie too close to their stars to be comfortable homes. In others, it has found hints of clouds, hazes, and complex molecules. Each detection is fragile, easily overturned by new data or more careful analysis, but the overall story they tell is robust. Atmospheres are delicate. They are heavy enough to shape everything a creature experiences on a planet's surface. They are light enough to be peeled away by the right combination of light and wind. When you breathe in, you are participating in one of the rarest balances the universe seems to allow. A planet of the right size, an atmosphere thick enough to hold warmth and water, thin enough to avoid crushing its inhabitants. A star quiet enough to allow that balance to last for billions of years. As we use Webb to describe atmospheres on worlds scorched, frozen, and stripped bare, that balance begins to look more special, not less. The more planets we see that fail, the more remarkable our own success appears. And just when you might be ready to conclude that the universe is stacked against gentle worlds, another set of observations arrives that complicates the picture even more. Farther out in space, and farther back in time, Webb is finding galaxies and black holes that grew far faster than our theories expected. If the rules that govern planets can be bent and twisted by stellar tempers, what happens when we push those rules to cosmic scales? The same telescope that reveals bare rock where we hoped for oceans is also uncovering monsters at the dawn of time and forcing us to ask whether the entire blueprint of the universe is stricter or stranger than we ever guessed. When you want to know how strict the universe really is, you go back to when it was young and ask how quickly it learned to build structure. For decades, the standard picture was fairly simple. After the Big Bang, matter cooled and condensed slowly.
Tiny ripples in density grew into clouds. Clouds merged into proto-galaxies, and over hundreds of millions of years those infants became the majestic spirals and ellipticals we see today. Massive black holes were supposed to arrive late in that story, as the products of many generations of stars and mergers. Then the James Webb Space Telescope started looking at the universe when it was only a small fraction of its current age, and the neat story began to fray. In deep fields where Hubble once saw only a few faint smudges, Webb revealed swarms of young galaxies. Many of them were more massive, more luminous, and more chemically enriched than theory expected so early. It was as if you opened a family photo album and found fully grown adults in the pictures from kindergarten.
The biggest surprises, though, were hiding in the very hearts of those early systems. In the nearby universe, there is a surprisingly tight relationship between the mass of a galaxy and the mass of the black hole that lives at its centre. Measure enough of them and you find a rough rule. Bigger galaxies get bigger central black holes. The black hole is usually only a tiny fraction of the total mass in stars. It is as if the galaxy and its central monster have grown up together over billions of years, feeding each other with gas and feedback. Cosmologists used that relation as a guide for how galaxies should evolve over time. Webb, peering back to a time when the universe was only a few 100 million years old, has found systems that break that pattern. In some small, young galaxies, the central black hole already rivals the mass of the entire galaxy in stars. The host looks like a faint smear, but at its core is a compact source blazing with energy as matter spirals into the black hole. It is like seeing a toddler with the heart of a giant athlete. The proportions feel wrong, and that wrongness tells you something important about how fast black holes can grow. One explanation is that the seeds of these early black holes were already enormous. Instead of starting as the remains of a single massive star, they may have formed when entire clouds of gas collapsed directly into black holes, tens of thousands of times more massive than our Sun. If those seeds then gorged on fresh gas in the dense early universe, they could reach supermassive sizes incredibly quickly. Another possibility is that they grew through runaway mergers, swallowing smaller black holes and dense star clusters in rapid succession. Either way, they challenge the idea that galaxy and black hole growth are always tightly coupled. Astronomers began to notice a particular kind of object in Webb data that embodied this puzzle. Tiny, compact sources that glowed fiercely in infrared, often reddened by dust, and appeared at extreme distances. Because of their small size and intense brightness, they were nicknamed little red dots. Some early analyses suggested that these might be very young, very massive galaxies full of newborn stars. If true, they would imply that the universe was capable of assembling enormous stellar systems far earlier than expected. Digging deeper, researchers realized that many of these dots looked more like overgrown black holes than bloated star factories. Their spectra carried the fingerprints of hot gas swirling in accretion disks, rather than the more distributed patterns of starlight. The radiation from the central engines was so intense that it outshone the surrounding galaxy, making it hard to tell how many stars were actually present. This is where the crisis headlines began. If these objects were truly both huge galaxies and huge black holes, our models of structure formation would be in serious trouble. The reality, as often happens in science, turned out to be more nuanced and more interesting. As teams refined their models and subtracted the glare of the active centers, some of the most extreme claims softened. Many of the early galaxies are still surprisingly massive and evolved, but not quite as fantastically huge as first thought. Some of the apparent monsters were partly illusions created by blended light, limited resolution, and the natural tendency of pioneering studies to push measurements to their limits. The universe was not completely breaking the rules we had written for it, yet the tension did not disappear. Even when you account for contamination from active black holes, you still find objects that are too bright, too compact, and too chemically developed for the time in which they live. Consider that heavy elements like oxygen, carbon, and iron are forged in stars and spread into space when those stars die. To see strong signatures of these metals in galaxies only a few 100 million years after the Big Bang means that many generations of stars have already lived and died there. It suggests a frantic early burst of star formation, as if the universe was in a hurry to grow up. You can picture this era as a kind of cosmic downtown district during a gold rush. Gas streams along filaments of dark matter into growing halos. As it hits the dense centers, it cools and collapses, lighting up in storms of starbirth. Massive stars blaze for a short time and then explode, stirring the gas and enriching it with heavier elements. At the same time, some of that gas funnels into the central black hole, which responds by blazing with radiation and launching winds that can blow material back out. Webb gives us snapshots of this frenzy frozen in time. By comparing these snapshots across different distances, astronomers can start to assemble a timeline. They see galaxies that look messy and clumpy, still assembling, and others that already show hints of rotation or ordered structure far earlier than expected.
They see central black holes that are overgrown compared to their hosts, and others that match the nearby relation more closely. Every new object is a piece of the puzzle, The overall picture is that the early universe was not a smooth, slow ramp up in complexity. It was a patchwork of extremes, with some regions running far ahead of schedule. One of the most powerful tricks Webb uses here is spectroscopy. When you spread out the light from a distant galaxy into a spectrum, you see bright and dark lines that correspond to specific elements and physical conditions. Certain line ratios tell you how hot the gas is, how dense it is, and whether it is being excited by young stars or by the harsh radiation from an accreting black hole. Other lines tell you how much dust is present and what the overall chemical richness looks like. It is like reading the vital signs of a patient across billions of light years. Some of Webb's spectra from high redshift galaxies show line ratios that only make sense if a central black hole is pumping energy into the surroundings. Others look more like pure star-forming regions. This diversity suggests that black holes and galaxies have a complicated relationship from the very beginning. In some systems, the black hole may be driving powerful outflows that choke off further star formation. In others, gas flows in without much interference, allowing the galaxy to grow quietly while the central engine slumbers. The simple picture of a single coevolution track gives way to many possible paths. It is hard not to feel a kind of vertigo when you contemplate this. Human beings evolved on a single planet around a single calm star. From that vantage point, we guessed at the history of the universe by extrapolating from a few nearby examples and computer models. Now a single observatory, parked far from Earth and cooled to just a few degrees above absolute zero, is sending back direct evidence that some of our guesses were not bold enough. The cosmos did not just build galaxies and black holes on time. In some neighbourhoods it seems to have done so with reckless speed. This rush has consequences for everything that comes later. The first generations of stars and black holes set the stage for reionization, the era when the fog of neutral hydrogen that filled space after the Big Bang was cleared by the first sources of light. They determine how quickly heavy elements become available to seed future planets. They influence how large-scale structures like galaxy clusters assemble, and how gas flows through the cosmic web. When Webb shows us an overgrown black hole in a small galaxy at early times, it is not just a curiosity. It is a sign that the energy budget of the young universe may have been very different from what we assumed. You might wonder what all of this has to do with the stability of planets and the habitability of worlds. The connection is not obvious at first, but it is real.
The heavy elements that make up rocky planets, water, and even the iron in your blood all come from earlier generations of stars. If the first galaxies form earlier and evolve faster, that means habitable planets might have started to appear sooner in some regions of the cosmos. On the other hand, intense early activity from black holes and starbursts may have bathed those regions in harsh radiation, making them less friendly to delicate chemistry. The same processes that enrich space can also sterilize it. As Webb continues to map these early systems, it is also testing the backbone of cosmological models, the distribution of galaxy masses, the way their brightness changes over time, and the abundance of very massive objects at high redshift all feed back into our estimates of how dark matter clumps and how dark energy stretches space. Already there have been debates about whether certain extremely luminous galaxies are too common for the standard model of cosmology. Each time, careful work has trimmed away some of the tension, but the nagging sense remains that the young universe may have more efficient pathways to growth than we have fully captured in our equations. There is a familiar pattern here. At first, new data comes in and seems to break everything. Headlines proclaim a crisis. Then researchers dig into the details, find sources of bias, improve their models, and some of the apparent conflict melts away. What is left is a subtler, more focused set of discrepancies. Webb has followed that arc already with its early galaxy discoveries. It has not demolished the foundations of cosmology. It has, however, carved fresh cracks into our picture of how quickly complexity can emerge and how tightly the lives of galaxies and black holes are bound together. This is good news if you care about learning how the universe really works. Tension between theory and observation is where progress happens. Each stubborn mismatch is an invitation to look again, to refine, to ask whether some hidden assumption has been taken for granted too long.
You can almost feel the collective mind of the field leaning toward these little red dots, these overgrown hearts in tiny bodies, asking what they're trying to tell us. As we listen, another pattern comes into focus. The early universe is not just a story of isolated systems growing in peace. It is a story of collisions, mergers, and violent encounters. Galaxies tug on each other, draw near, and sometimes pass through one another in slow-motion catastrophes that stretch over hundreds of millions of years. Webb has caught some of these interactions in their youth, revealing tangled streams of gas and newborn star clusters where two galaxies are beginning to collide.
If black holes can grow so fast in small hosts, what happens when their galaxies crash together and their central monsters are forced into the same gravitational well? The answer to that question is not just an abstract curiosity. It leads directly into one of the most dramatic processes that shape the universe on large scales, and one that will eventually reshape our own galaxy. To follow that trail, we need to step back from the tiny, bright cores and look at the full lives of galaxies, from chaotic youth to quiet maturity, and through the violent events that can shut them down or transform them forever. When you zoom out from the tiny, blazing cores that Webb reveals, a different pattern begins to appear. Galaxies are not static islands of stars. They are weather systems on scales so large that light itself needs tens of thousands of years to cross them. They are born in chaos, struggle through violent youth, and sometimes settle into something that looks calm, only because we are too far away to see the constant motion. To understand how they live and die, we have to learn to read that motion in the faintest smears of light. On familiar pictures from ground telescopes or from Hubble, a galaxy can look almost tranquil. A neat spiral, arms traced with blue young stars, a soft golden core. Webb breaks that illusion by slicing the light into many narrow colours and measuring how each one shifts. If gas is rushing toward us, its lines move slightly one way. If it is flowing away, they move the other. Lay those measurements over the image, and suddenly the galaxy becomes a map of streaming, colliding, and churning matter. In many of the earliest galaxies Webb can see, that map is messy. Instead of graceful rotation, you find gas clouds flying in all directions. Some regions are forming stars at furious rates, while others are almost empty. It looks less like a disk calmly spinning in space, and more like a storm that has just begun to organise. Giant clumps crash together, compressing gas and sparking new clusters of stars. Supernova explosions punch hot bubbles into the surroundings. The whole structure flickers and seethes. You can imagine living in one of those clumps. Your night sky would be packed with bright young stars and glowing gas. Gravity would be pulling on your entire neighbourhood as it migrates through the larger galaxy. Over millions of years, your patch might stretch into a spiral arm, fall toward the centre, or be torn apart entirely. From the quiet vantage point of the Milky Way today, it is easy to forget that galaxies are not born as the tidy structures we hang on classroom walls. They have to fight their way into that shape. As time passes in the universe, some galaxies manage to settle. Gas cools and falls into a rotating disk. Star formation spreads out into broad lanes instead of concentrated knots. Webb sees hints of this order even in quite young systems. It detects smooth velocity gradients that tell us gas is moving mostly in a single direction, like traffic flowing around a ring road. These are the ancestors of the grand design spirals we admire nearby. But even they carry scars of a rough past. Warps in their disks, streams of stars left over from swallowed companions, tails of gas reaching into intergalactic space. There is another kind of galaxy that Webb has started to reveal more clearly. Galaxies that burned hot and then went quiet. They are sometimes called quenched or quiescent systems. Their stars are old and red. Their gas reservoirs are depleted or heated so that it cannot easily collapse into new stars. In the nearby universe, we see many massive elliptical galaxies in this state. What surprised astronomers was to find similar, dead-looking galaxies much earlier in cosmic history than expected. To shut down star formation in a young galaxy, something has to remove or disturb its gas. One suspect is feedback from the central black hole. When matter falls into that black hole, it releases enormous energy. Some of that energy emerges as jets that pierce out of the galaxy, others as winds that push in every direction. Webb and other observatories see signs of such outflows in the form of broadened spectral lines and strange gas motions. It is as if the galaxy has managed to light a fire in its own heart that then blows away its fuel. Not every quiescent galaxy shows clear evidence of this kind of active central engine. In some cases, dense environments may do the job instead. Galaxies in clusters can be stripped of their gas as they plough through the hot medium that fills the cluster. Tidal forces from close encounters can distort and disturb them until their star-forming regions are torn apart. The result, whether driven from within or without, is the same. A galaxy that once blazed with newborn stars now drifts through space as a population of aging suns and compact remnants. There is a strange beauty in these dead giants. Their light is smooth and uniform. Their shapes can be almost featureless ellipses. Yet inside them, stars remain in motion, orbiting the centre in complex paths. Many of them will eventually end as white dwarfs, neutron stars, or black holes.
When you look at one of these quiescent galaxies through Webb, you are looking at a fossil record of a storm that has already passed. The drama lies in the past, but its consequences echo forward. Galaxies do not live these lives alone. Gravity pulls them toward one another. The same dark matter filaments that funneled gas to feed early starbursts also guide whole galaxies into groups and clusters. When two galaxies draw near, their mutual pull stretches out long arms of stars and gas. Webb has captured many such moments in exquisite detail. You can see delicate bridges of material arcing from one galaxy to another. You can see fireworks of star formation igniting in the compressed regions where their gas clouds collide. If you could speed up time, a galaxy merger would be one of the most spectacular events you could witness. At first, the two systems pass through each other, their stars mostly missing direct collisions because of the vast distances between them. But their gas does not pass so easily. It slams together, slows down, and falls inward. Tidal forces scramble orbits, turning ordered disks into warped, twisted shapes. Over hundreds of millions of years, the galaxies may swing around and pass again, each encounter leaving them more distorted than before. Eventually, the dance ends in a coalescence. The two cores sink toward each other through a process called dynamical friction, losing energy as they stir up the background of stars.
In the middle, two supermassive black holes that once sat at the centres of separate galaxies now find themselves orbiting together inside a single swollen remnant. This is not just a curiosity hidden behind light years of dust, it is a laboratory for one of the most powerful events in the universe. Webb has found examples of galaxies in this in-between state. Systems where spectra reveal two distinct active nuclei, slightly offset in position and in velocity. Each nucleus carries the signature of a feeding black hole. The surrounding gas glows with excited emission lines. In some images, you can even see distinct tidal tails sweeping out, proof that a recent close encounter has taken place.
These are the precursors of supermassive black hole mergers, the seeds of future gravitational waves with extremely long wavelengths. Those waves are so gentle by the time they reach us that we cannot feel them directly. Instead, radio observatories use pulsars as cosmic clocks, looking for tiny irregularities in their signals that betray a background hum of low-frequency gravitational waves from many such mergers across the universe. When Webb pinpoints pairs of supermassive black holes in galaxies that are on the verge of combining, it is effectively identifying the individual instruments in an orchestra whose music we will hear as that gravitational background. It is worth remembering that our own Milky Way is not exempt from any of this.
Far away in the night sky, the Andromeda Galaxy drifts toward us at hundreds of kilometers per second. In a few billion years, the two disks will begin to overlap. Tidal forces will stretch out long streams of stars. New star formation will flare where gas clouds slam into each other. Eventually, the central black hole of the Milky Way and the central black hole of Andromeda will spiral together in the same kind of slow, magnificent dance that Webb now observes in distant systems. From the perspective of any future civilizations that might be watching, this will be a terrifying and beautiful time. Familiar constellations will warp and dissolve as stars are thrown into new orbits. The night sky will fill with strange arcs and knots of light. Some stars will be flung into intergalactic space as runaways. Others will be drawn deep into the growing core. Yet even through all of that, most individual solar systems will likely remain intact. The emptiness of space between stars is so vast that direct collisions are rare. Still, the long-term fate of star formation in the merged galaxy depends on how the gas behaves. If enough gas survives and cools, new generations of stars and planets will continue to form. If feedback from the combined central black hole or the violence of the merger heats or expels too much gas, the new galaxy could quench and fade. The line between a living, star-forming system and a dead red remnant can be drawn by events that play out over scales almost impossible to grasp.
When you step back, another theme appears. The most violent processes in galaxies are also the ones that create the ingredients for worlds like ours. Supernova explosions from massive stars produce heavy elements and spread them into space. Black hole outflows can push enriched gas out of galaxy centers into wider regions, where it can later cool and form new stars with rocky planets. Collisions and mergers stir and mix everything, preventing matter from sitting too comfortably in one place. Without that churn, there might be fewer planets, fewer chances for chemistry to arrange itself into something we would recognize as life. It is a hard idea to sit with. The same cosmic violence that can shut down star formation and turn galaxies into graveyards also forges the elements in your bones.
The same black holes that can choke galaxies may help seed the conditions that allow planets to exist at all. Webb, with its ability to see dusty starbursts, quiet, quenched systems, and merging cores in one consistent framework, is pushing us toward a more honest view of that balance. Creation and destruction on galactic scales are not separate stories. They are different faces of the same process. As you hold that thought, picture again the swirling chaos in early galaxies, the graceful disks that emerge from that tumult, the silent giants that have already burned through their fuel, and the colliding systems where two glowing hearts share a crowded core. Each stage writes new chemical and dynamical possibilities into the universe. Each stage decides how much gas remains, where it goes, and what kinds of stars and planets can form from it. If you follow those decisions down in scale, they eventually arrive at something very small, a single star, a single world. And not every world ends up where it began. When galaxies collide and clusters evolve, many stars are nudged into new paths. Some are stripped from their homes entirely. Planets can be shaken loose from their parent stars by close encounters or by the slow broadening of orbits as systems lose mass. That raises a strange possibility that Webb is now beginning to explore directly. The universe may be filled with worlds that drift without suns, born in the hearts of galaxies and then cast into the dark, carrying with them all the heavy elements and complex chemistry that those violent galactic lives produced. Imagine a planet wandering between the stars, with no sunrise and no sunset. There is no familiar arc of a sun across the sky, no dawn, no dusk, only a night that never ends. If you stood on its surface and looked up, you would see nothing but the scattered light of the galaxy, the Milky Way rising and setting only because your planet spins, not because it orbits a star. The air, if there is any, would glow faintly with the heat leaking from the planet's interior. Everything else would be cold, black, and silent.
For a long time, these worlds existed mostly in theory. Now, with telescopes like Webb and its companions, we're starting to find them. Their story begins inside the crowded nurseries where stars are born. Giant clouds of gas and dust collapse under gravity, fragmenting into clumps. Most of those clumps grow into stars, some large, some small. Around them, leftover material flattens into disks where planets slowly assemble. It is a messy process. Planets can be hurled inward or outward by gravitational tugs. Some spiral into their stars, others are flung completely free, ejected into interstellar space as unwanted children. In a universe where galaxies collide and clusters evolve, there are many ways to create a planet that ends up alone.
We first guessed at their existence by following the math. If planetary systems are common, and if their early histories are chaotic, then ejections should happen often. Some estimates suggested that for every star-bound planet like Earth, there might be one or more rogue worlds drifting in the dark. But guessing is not the same as seeing. These planets do not shine by their own light, except for a fading glow of internal heat. They are too small and cold to show up in most surveys. To find them, we had to learn to watch how their gravity bends light from objects far behind them. This is the technique called microlensing. If a compact object passes in front of a distant star, its gravity acts like a weak lens. For a short time, the background star appears slightly brighter as its light is focused. The pattern and duration of that brightening depend on the mass and speed of the lensing object. In many cases, that object is another star with its own planets. In some cases, though, the lens appears to have the mass of a planet, but no detectable star along with it. That is our first hint that we are seeing a free-floating world. Surveys toward dense star fields, such as the central bulge of the Milky Way, have turned up these odd, short microlensing events. The timescales are too brief for normal stars. The signals look exactly like what you would expect from a lonely planet drifting between us and a distant background sun. These detections are rare, but they are enough to show that rogue planets are not just a theoretical curiosity. They are out there, in significant numbers, invisible except when their gravity announces them for a few hours or days. Closer to home, in star-forming regions like the Orion Nebula and other young clusters, Webb and ground-based telescopes have found faint, cool objects that sit at the edge between planets and stars. Some of them have masses similar to Jupiter. They shine weakly in infrared because they are still warm from their recent birth. Many appear to float free, not bound to any bright star. Even more surprising, some show hints of dusty disks around them, the same kind of structures we see around young stars. It is as if the universe is building miniature planetary systems that orbit nothing at all. That thought feels almost paradoxical. We are used to thinking of planets as things that circle stars. Here we have objects that by mass and temperature look like planets, but by behaviour look like tiny stars, complete with their own disks. Whether you call them planetary mass objects, sub-brown dwarfs, or something else, they remind us that nature does not care about our neat categories. If there is enough gas in the right place, gravity will make a sphere. Whether that sphere orbits a star, or lives alone, or sits just below the threshold of starhood, is a detail of local history. Brown dwarfs occupy that threshold.
They are too small to sustain steady hydrogen fusion like true stars, but too large to be ordinary planets. For a time after birth, they burn a heavier isotope of hydrogen in their cores, then slowly cool and fade. Webb has been particularly good at finding and characterizing these failed stars, especially the coolest ones. In some regions, they may be as numerous as normal stars, maybe more. Add in all the rogue planets that weigh less than a brown dwarf, and you start to realize that the galaxy may be filled with dim, unnoticed masses. This swarm of cold objects matters for more than our curiosity. For years, astronomers have been trying to account for all the mass they know must be present from the way galaxies rotate and clusters hold together. A large fraction of that mass clearly comes from something we call dark matter, a component that does not interact with light at all. But another part of the puzzle is more mundane. Normal matter can hide in forms that are simply hard to see. Gas, dust, faint stars, brown dwarfs, rogue planets, and compact remnants all contribute to what is sometimes called the missing baryon problem. By counting brown dwarfs and free-floating planetary mass objects, Webb is helping to narrow that gap. Each new census of a star-forming region gives us better statistics on how often gravity chooses to make a star, a failed star, or a planet-sized body. The numbers so far suggest that these dim populations do carry significant mass, but not enough to explain away dark matter.
Instead, they sit in an interesting middle ground. They are important for the local ecosystems of galaxies, shaping how gas cools and stars form, but they cannot take over the role of the invisible scaffolding that holds large-scale structure together. If you think on smaller scales, though, their significance changes. A brown dwarf with a few Jupiter masses may host its own planets or moons. A lonely Jupiter mass object may carry a retinue of smaller companions. These are not just chunks of rock and gas with no internal story. They can have weather, storms, chemistry in their atmospheres, and perhaps buried oceans beneath ice layers if they have moons. Most of them will never see starlight as anything more than a faint glow from distant constellations. Yet they could be stable for trillions of years, quietly cycling heat from their interiors into surrounding space. Consider what that might mean for habitability. We tend to fixate on the habitable zone around stars, that narrow band where liquid water can exist on a planetary surface because starlight warms it just enough. But there are other ways to keep water liquid. Tidal heating from gravitational tugs can warm the interior of a moon. Radioactive elements in a planet's core can generate heat for billions of years. Thick insulating ice can trap that heat, allowing oceans to exist far below the surface, even in deep space. In that sense, a rogue planet with the right composition might host subsurface seas that endure far longer than any surface ocean on an exposed world. Moons around gas giants in normal star systems give us a template. Europa at Jupiter and Enceladus at Saturn both show evidence of global oceans under ice, kept warm by tidal flexing and internal heat, not by sunlight. Pluck a similar moon away from its parent star, bury it in darkness, and it might still keep its ocean. Give a rogue planet a thick, hydrogen-rich atmosphere, and it could trap internal heat even more efficiently, turning its surface into a dimly lit, warm environment under a perpetual black sky. To any life there, stars would be distant curiosities, not essential sources of energy. We do not know whether such biospheres exist. They are speculative, but grounded in physics we already understand. What Webb and other telescopes contribute here is not a direct detection of life, but a growing realization that the universe is very good at making the raw platforms where exotic habitats might arise. Rogue giants with disks, brown dwarfs with worlds, planet-sized bodies everywhere that gravity has had the opportunity to gather gas and dust. It shifts the question from whether planets can exist without stars to how many ways matter can arrange itself into long-lived, energy-rich environments. There is another, more emotional layer to this. When you imagine a rogue planet drifting through the galaxy, it is hard not to feel a sense of loneliness. No sunrise, no path around a familiar point, only endless night. Yet from a cosmic perspective, these worlds are not lost. They are part of the same flow of matter that builds stars, galaxies, and everything in between. Some were born in clusters that have since dissolved. Others were ejected during violent reshufflings in crowded systems. They carry with them metals forged in ancient supernova explosions, dust shaped by dying stars, ice enriched by generations of chemistry. Webb has revealed that in young clusters such as NGC 1333, systems of two planetary mass objects can even form in pairs. Imagine two Jupiter-like bodies, each with a few times the mass of our giant planets, orbiting each other far from any star. They glow faintly in infrared, their mutual gravity binding them together like a miniature binary system adrift in the dark. There is something almost poetic in that image. Even in the loneliest parts of space, gravity finds ways to create partnerships. As we map these populations, a practical question emerges as well. Could any of this help explain odd signals in our measurements of the universe on larger scales? When you add up the contributions from all the cold, compact objects Webb can see or infer, you do get closer to the total amount of normal matter expected from early universe physics. Filaments of gas that once seemed empty turn out to contain more structure. The census of brown dwarfs and rogue planets grows. But there remains a stubborn gap that still demands truly dark matter, something beyond all the bodies we can photograph or weigh directly. In a way, this is freeing.
If rogue planets and failed stars cannot solve the entire missing mass problem, we can stop forcing them into that role and appreciate them for what they are. They are furniture in the cosmic house, rather than the hidden beams. They shape local neighbourhoods, influence how gas cools, and provide potential footholds for chemistry. They are part of the rich detail layered on top of the deep, simple gravitational field created by dark matter. Webb's gift here is to turn what was once invisible background into a population of objects we can study in their own right. If you step back from the technical details, an interesting symmetry appears. At the larger scales, we use tangled webs of galaxies, their motions and their light to understand invisible matter. At the smallest astronomical scales, we use tiny blips in a single star's brightness to infer the presence of a drifting planet. In both cases, gravity is the messenger. Webb sits between those scales, sensitive enough to pick up faint heat from lonely worlds and to dissect the light from early galaxies where black holes and stars are locked in a furious race to grow. All of this circles back to a simple, deep question. When heavy elements are forged in the violent lives of stars, where do they end up? Some stay in gas clouds that form new generations of suns. Some get trapped in long-lived brown dwarfs and planets that never see starlight again. Some are strewn into the outskirts of galaxies or flung into intergalactic space.
Each atom of carbon in your body could have spent billions of years cycling through these different reservoirs before landing on a planet that happened to sit at the right distance from a quiet star. Once you see the universe this way, as a constant exchange between light-bathed worlds and starless wanderers, between bright galaxies and dark scaffolding, another layer of the cosmic life cycle comes into focus. Stars and planets are not just born from clouds and return to them, they are shuffled, ejected, and hidden, populating the galaxy with a vast, unseen underclass of cold objects. It is tempting to think of these as endpoints, the quiet ash of cosmic activity, but in reality, they are seeds. Under the right conditions, they can host chemistry, retain heat, and perhaps even build complexity of their own. The same forces that scatter planets and build rogue worlds also create the explosions that fertilize space with heavy elements. Supernovae, gamma-ray bursts, and the deaths of the first stars are not separate from the story of dark planets. They are the events that set the initial conditions, that decide how many metals go into each new generation of bodies. To follow that trail, from the guts of massive stars to the ice of drifting planets, we have to watch how stars die and what they leave behind. That is where Webb turns next, tracing the final acts of stellar lives and the shockwaves that ripple out to shape future worlds. When a star dies, the universe does not look away. It writes that death in light and dust and shockwaves that ripple out for millions of years. If you could compress the history of a galaxy into a few minutes, you would see stars flaring into existence, burning hard, and then ending in flashes that briefly outshine everything around them. Those flashes are not just dramatic endings. They are the moments when raw hydrogen and helium are transformed into the heavier elements that build planets, oceans, and eventually, living cells. To trace that story, Webb has been turning its gaze towards stars on the edge of disaster and to the relics they leave behind. Some of the most important deaths begin very quietly. A red supergiant sits in a distant galaxy, swollen and cool, its outer layers puffed up like an enormous ember. Through most telescopes, it is just another point in a crowded field. Through Webb, that same point becomes a rich spectrum full of information. You can see the star's temperature, its dust, even hints of how much mass it has already shed into space. When astronomers compare earlier images with later ones, they sometimes find that such a star has vanished and a supernova has taken its place. By catching these progenitors before they explode, Webb is helping to fill in the missing frames in the film of stellar life. One of the surprises is how often dust hides the key actors from view.
Massive stars in their final stages can surround themselves with thick shells of material shed through winds and eruptions. In visible light, this dust can block almost everything, turning a bright star into a faint smudge, or erasing it entirely. Infrared light can slip through more easily. Webb's instruments, tuned to these longer wavelengths, have revealed red supergiants and other evolved stars that were simply invisible to earlier surveys. That means for years we were undercounting the very stars most likely to explode. This has consequences for how we see the universe. Supernovae are used as distance markers, as tools to map the expansion of space. They enrich their surroundings with heavy elements. They carve bubbles in the interstellar medium where new stars will later form. If we have been missing whole categories of dying stars because of dust, then our sense of how often galaxies recycle their material is off. Webb's detections of hidden progenitors help correct that bias, showing that some of the most important explosions begin in places we were literally blind to. Very close to home, one red supergiant has captured public imagination more than any other. Betelgeuse, the bright star on Orion's shoulder, is one of the most familiar points in the night sky. It is also a massive, unstable star in a late stage of its life. A few years ago it dimmed dramatically, causing a wave of speculation that it might be about to explode. Webb and other observatories helped reveal a more subtle and instructive story.
The dimming was caused by a cloud of dust that the star had belched out, which then cooled and condensed in our line of sight. In Webb's infrared eyes, Betelgeuse did not simply fade, it changed character, showing patterns that betrayed the newly formed dust. This told astronomers that the star's outer layers are more turbulent than they had realised, prone to large mass ejections that can briefly cover its surface. It was not the final collapse, but it was a clear sign that the star is restless and shedding material at a high rate. When Betelgeuse finally does explode, it will be an event bright enough to be seen in daytime. For now, we are watching it practice for that final act. The dust it throws off will not go to waste. Over time, those particles drift into the interstellar medium, joining the debris of other dying stars. Supernova explosions will later shock and compress that material, breaking some grains and forging others. The universe is constantly grinding and reheating this mixture, creating a complex soup of elements and molecules. Webb's sensitivity to dust emission makes it a powerful tool for studying this cycle. In supernova remnants, it can map where fresh dust forms as the blast wave ploughs into surrounding gas. In distant galaxies, it can see the glow of dust warmed by newborn stars, tracing how quickly heavy elements are being produced. Some deaths are more extreme than others. Occasionally, a massive star collapses in a way that channels much of its energy into narrow jets that punch through its outer layers and blast into space at nearly the speed of light. To us, these are gamma ray bursts, sudden flashes of high-energy radiation that arrive without warning. For a few seconds, they can outshine the rest of the observable universe in gamma rays. After that initial spike, they fade through X-rays, visible light, and infrared. Chasing that fading glow is one of the things modern observatories do best. Webb has joined this chase, turning its mirror toward the afterglows of gamma ray bursts in distant galaxies. In at least one case, its observations revealed a supernova emerging in the same place where the burst originated. The afterglow faded, but a slower rising bump in the infrared light signaled the birth of an expanding cloud of debris, rich in heavy elements. This confirmed what many suspected. Some gamma-ray bursts are not exotic separate events. They are the most energetic form of core collapse supernova, oriented so that their jets point almost directly at us. These explosions do more than light up a patch of sky. The shock waves they send out can compress nearby clouds, triggering new rounds of star formation. The elements they synthesize, including some of the heaviest in the periodic table, are flung into space where they can be incorporated into future planets. At the same time, their intense radiation can strip atmospheres from any unlucky worlds nearby and sterilize large regions for a time. Life and death on cosmic scales are deeply intertwined. The same explosion that seeds a galaxy with the building blocks of biology can also temporarily shut down the very process it enables. To understand where this cycle began, astronomers have long hunted for the first generation of stars. These hypothetical objects, often called population 3 stars, would have formed from nearly pure hydrogen and helium. With no heavy elements to help cool the gas, they are expected to have been very massive and very short-lived. None should remain today. The only way to find them is to look back far enough in time, or to search for their fingerprints in the chemical patterns of later objects.
Webb cannot resolve individual population 3 stars directly yet, but it can look for their influence in the neighbourhoods of ancient quasars and in the most distant galaxies it can see. If an early region was enriched only by these first stars, its gas would show a very particular mix of elements. Certain lines in the spectrum would be strong or weak compared to regions enriched by later generations. By measuring these line ratios, astronomers can infer whether they're seeing the products of primordial explosions or a blend of many later ones. Some Webb observations have revealed surprisingly pristine pockets of gas, with very low metal content even in galaxies that otherwise look evolved.
Others show odd abundance patterns that fit better with models of extremely massive early stars than with more ordinary populations. Each of these is a clue. Together, they are helping to outline when and where the universe first began to move beyond simple hydrogen and helium into a richer chemical palette. That transition marks the birth of the conditions required for rocky planets and complex molecules. On more human scales, it is hard not to feel a personal connection to this chemical story. The calcium in your bones, the iron in your blood, the oxygen you breathe, and even much of the carbon that forms your cells were all forged inside stars and scattered by their deaths. Some came from gentle winds off red giants. Some came from violent core collapse supernovae. Some came from rarer, even more extreme events where neutron stars collided and sprayed heavy elements into space. Webb's observations of supernova remnants, gamma-ray burst afterglows, and dusty star-forming regions are like a series of flashbacks showing where those atoms have been. Once you see things that way, the universe stops being a static backdrop and becomes a kind of giant foundry. Clouds collapse into stars. Stars cook new elements. Explosions distribute them. New clouds enriched by this material form new stars and planets. On those planets, chemistry explores more and more complicated structures, eventually giving rise to organisms that can look back and piece together the story.
Webb is giving us sharper images of each stage in that cycle, especially the ones that were hardest to see in visible light because of dust. There is also a practical payoff to understanding stellar deaths in detail. Different types of supernova leave behind different compact remnants. Some collapse into neutron stars, others into black holes. The distribution of these remnants affects everything from the gravitational wave background to the way galaxies light up in X-rays. It also sets the inventory of exotic objects that later generations of telescopes may find. Webb's ability to pinpoint the exact kind of explosion in a distant galaxy by reading its spectrum and light curve in infrared helps refine our models of what kinds of remnants are being produced and where they end up.
In nearby galaxies, Webb has imaged star-forming regions where massive young stars are still embedded in their birth clouds. It can see protostars with jets, clusters barely emerging from their cocoons, and cavities carved by earlier generations of winds and supernovae. Put together, these scenes show that stellar birth and death are tightly interwoven. New stars are born in shells and knots shaped by old ones. The places that look most chaotic and dangerous are often the most fertile. The raw material for future planetary systems is concentrated in the very regions where massive stars will eventually explode. You might expect that as we fill in this picture, everything would become more predictable. In some ways it does. We can better estimate supernova rates, dust production, and chemical enrichment histories. In other ways, the new data only deepen the mystery. Webb has shown that some stars explode in ways that produce far more dust than expected, while others seem oddly clean. Some remnants glow brightly in infrared as their shock waves encounter dense pockets of gas, while others fade quickly. The diversity is greater than many models anticipated. That diversity matters when we look beyond individual galaxies and try to track how energy and matter move through the entire cosmos. The timing and strength of stellar feedback help determine how gas flows in and out of galaxies, how quickly they form stars, and when they shut down.
The number of compact remnants influences the gravitational tug on surrounding matter. The distribution of heavy elements, including those that can cool gas efficiently, shapes where new stars can form. Webb's detailed view of stellar deaths feeds directly into the larger questions about how galaxies evolve and how the cosmic web changes with time. What makes all of this especially compelling is that we're not just mapping distant fireworks. we are retracing the history that made our own existence possible. The atoms that currently sit in your body once rode shockwaves through interstellar space, floated in cold clouds, froze onto dust grains, and were baked off again. They cycled through different structures and environments until they ended up on a world with the right atmosphere and temperature. That world then spent billions of years under a steady sun, while chemistry experimented with increasingly complex self-sustaining patterns. As Webb continues to catch stars in the act of dying and to read the chemical fingerprints of their debris, it is refining our sense of how often such a chain of events can play out. It shows us regions where heavy element production is rapid and others where it lags. It reveals galaxies where star formation has shut down early, locking heavy elements into aging stars, and others where the cycle is still raging.
Each new piece of data nudges our estimates of how many planets like Earth might exist, and how often the conditions for life are assembled. Yet even as we get better at tracking this chemical and dynamical history, there are deeper questions that remain stubborn. When we use supernovae as distance markers to measure how fast the universe is expanding, different methods give slightly different answers. Webb's role in refining those measurements has highlighted, rather than erased, that discrepancy. The same telescope that shows us how stars live and die is now pointing to cracks in the larger framework we use to describe the cosmos. To follow that thread, we have to step back once more from individual explosions and rogue planets and look at the numbers that govern the expansion of space itself. When you try to describe the universe as a whole, you end up needing a single number that tells you how fast space itself is stretching. That number is called the Hubble constant. It tells you how many extra kilometers per second of recession speed you get for every megaparsec of distance. In principle, it should be one of the most solid measurements in cosmology. In practice, it has become a fault line. Different ways of measuring it give different answers, and the more precise those measurements become, the more stubborn the disagreement looks. One way to find this number is to look at the baby picture of the universe. The early cosmos was a dense, hot plasma, and sound waves rippled through it. When that plasma cooled enough for atoms to form, light decoupled and began to travel freely. We see that light today as the cosmic microwave background, a faint radio glow that fills the sky. Its tiny fluctuations encode how much matter and radiation existed in the early universe, how they clumped, and how gravity pulled on them. By fitting a model to those patterns, you can infer how fast the universe must be expanding today. Another way to find the Hubble constant is to build a ladder from nearby distances out to the depths of space. You start with objects whose distances are known from geometry. You then calibrate slightly more distant objects based on those, and so on. One key rung on that ladder is made of variable stars, called Cepheids, whose brightness pulses with a period that depends on their true luminosity. Another rung rests on Type 1a supernovae, explosions that act as standardizable candles because their peak brightness can be inferred from the shape of their light curves. Measure how bright these objects appear, compare that to how bright they should be, and you get distance. Combine distance with recession speed from redshift, and you get the local expansion rate. For years, the early universe method and the local ladder method have disagreed. The value inferred from the cosmic microwave background is lower. The value from Cepheids and supernovae is higher. The difference is not huge in everyday terms, on the order of 10%. But in precision cosmology, a 10% disagreement that does not go away as you improve your instruments is a blaring alarm. You can feel the tension in that gap. Either hidden systematics lurk in one or both measurements, or the model that ties them together is missing something important. Webb entered this dispute not by inventing a new technique, but by sharpening one of the existing ones. If there was a flaw in the local ladder, it might lie in the way we observe Cepheids in galaxies that also host Type 1a supernovae. Hubble Space Telescope data had already been used to measure those Cepheids and calibrate the supernova distances. Some critics wondered whether crowding, dust, or subtle calibration issues might be biasing those measurements upward, making distances seem slightly shorter and the expansion rates slightly faster than they really are. With its larger mirror and infrared sensitivity, Webb could revisit the same galaxies and look for the same Cepheids with greater clarity. Infrared light suffers less from dust extinction. The higher resolution means background contamination from nearby stars is easier to separate. If the Hubble result was artificially high, Webb should have seen cleaner Cepheid signals that, when plugged into the ladder, nudged the Hubble constant downward toward the cosmic microwave background value. That did not happen.
When teams used Webb to re-observe Cepheids in multiple supernova host galaxies, they found that the new data lined up almost perfectly with the earlier Hubble measurements. The scatter decreased, the individual distance estimates improved, but the overall scale, the one that feeds into the local Hubble constant, stayed essentially the same. The problem did not dissolve under better data, it crystallized. The universe really does seem to be expanding faster when measured nearby than when inferred from its earliest light. You can think of this as two clocks ticking at slightly different rates. One clock is set by the physics of the early universe, the other is set by the rhythms of present-day galaxies and explosions. If both clocks used exactly the same mechanism, they should stay in sync.
The mismatch suggests that either we misunderstand one of the mechanisms or something changed in between. Webb's confirmation of the local ladder result pushes us toward the second possibility. It is as if the cosmos is whispering that the rules may have shifted slightly over billions of years. One family of ideas blames dark energy, the mysterious component that seems to be driving the accelerated expansion of space. In the simplest model, dark energy is a constant property of space itself. Its relative importance grows as the universe expands, but its nature does not change with time. If that assumption is wrong, and dark energy evolves or interacted differently in the early universe, you could reconcile the two Hubble values. Another family of ideas adds new particles or forces that briefly altered the balance in the early plasma before fading out. A third possibility tinkers with gravity itself on cosmic scales. Webb cannot see dark energy directly, no telescope can yet. What it can do is map how structures grow over time. The distribution of galaxies at different redshifts, the amount of clustering on various scales, and the abundance of massive objects at early times all respond to the background expansion history. If dark energy changes with time, that change leaves fingerprints in these patterns. Combined with other surveys, Webb's data can tighten the noose around various exotic explanations, ruling out some and squeezing others into fine-tuned corners.
While this is happening on the side of dark energy, another set of questions is swirling around dark matter. We infer its presence from the way galaxies rotate, from the motions of clusters, and from the lensing of background light. Without some extra mass, visible matter alone cannot explain these effects. In the standard model of cosmology, dark matter is a cold, collisionless component that clumps and forms the scaffolding on which galaxies build. That picture has been extremely successful at explaining large-scale structure. But at smaller scales, cracks and quirks appear. Some dwarf galaxies show rotation curves that rise and then flatten more gently than simple, dark matter simulations would predict. Others have dense central concentrations that look more like cusps.
The number of small satellite galaxies around some galaxies differs from naive expectations. Astronomers have long debated whether these issues point to new properties of dark matter or simply to the messy influence of normal matter, such as stellar feedback blowing gas out of small galaxies and reshaping their dark matter halos. Here too, Webb plays a role. By measuring the star formation histories, chemical abundances, and internal motions of stars in dwarf galaxies, it helps disentangle how much of their structure is shaped by internal processes versus invisible mass. In some systems, strong outflows from supernovae and stellar winds appear capable of puffing up the central dark matter distribution, turning sharp cusps into flatter cores.
In others, especially very faint dwarfs, the imprint of feedback is weaker, and the raw behaviour of dark matter stands out more clearly. Each case is a test of how far standard dark matter can be stretched before it breaks. At the same time, Webb's census of dim objects inside galaxies touches the boundary between normal matter and dark matter. Brown dwarfs, rogue planets, compact remnants like white dwarfs and neutron stars all contribute mass without much light. For a while, it was tempting to imagine that perhaps a significant fraction of what we call dark matter might really be a swarm of these faint bodies. Microlensing surveys and detailed dynamical studies have largely ruled that out. There are simply not enough such objects to account for the missing mass. Webb's counts support that conclusion. In star-forming regions where its infrared vision can pick out the faintest young objects, the number of brown dwarfs and planetary mass bodies is impressive but not overwhelming. They matter for local dynamics and for the way gas cools and fragments. They do not add up to the colossal budget dark matter requires. Normal matter in hard-to-see forms can fill in some missing pieces, but not the entire puzzle. There remains a component that does not emit or absorb light in any way we have yet detected. You might feel a strange combination of satisfaction and discomfort at this point. Satisfaction, because multiple lines of evidence, from galaxy rotation to gravitational lensing to Webb's deep surveys, point consistently to the same story. There really is a vast reservoir of invisible mass out there. Discomfort because we still do not know what it is. The universe keeps passing every test we throw at it with the same answer, and that answer is a shrug in the language of particle physics. The Hubble tension wraps another layer around that unease. The standard cosmological model that uses cold dark matter and a simple dark energy component has been spectacularly successful. It predicted many features later confirmed by observation. It fits the cosmic microwave background and large-scale structure beautifully. Now, with Webb's precise support for the local expansion rate, that same model is under pressure. It has to accommodate a universe that seems to expand one way when you look far and another way when you look near.
Sometimes people ask whether this means cosmology is in crisis. It might be more accurate to say that cosmology is at an interesting crossroads. The foundations are solid, but there are cracks in the plaster. You could patch those cracks with small adjustments, like slightly different neutrino physics or subtle early dark energy episodes. Or you could treat them as hints that a deeper renovation is coming. Webb, by refusing to make the cracks go away, is gently pushing us toward the second mindset. It is telling us that the universe is not quite as simple as the neat diagrams in textbooks. There is another number that quietly haunts these discussions. It is the fraction of the universe that is made of the kind of matter you and I are familiar with. Protons, neutrons, electrons, all the atoms that can form stars, planets, gas, dust, and living things. That fraction is surprisingly small, on the order of a few percent. The rest sits in dark matter and dark energy. Even within that small slice of normal matter, a significant portion does not live in stars. It floats in diffuse gas between galaxies, in warm and hot filaments that thread the cosmic web. Webb has been helping to track down this missing normal matter by observing absorption lines in the spectra of distant quasars and by imaging the faint glow of gas in intergalactic filaments. Heavy elements in that gas act as tracers, revealing where past generations of stars have enriched the medium. In some cases, Webb sees signs of galactic winds blowing metals far into intergalactic space. In others, it detects cool clumps condensing along filaments like dew on spider silk. Piece by piece, the census of where baryons live becomes more complete. The picture that emerges is one in which normal matter is busy and mobile. It falls into galaxies, forms stars, is blown back out, and slowly drifts along the large-scale structure carved by dark matter. Dark matter itself shapes the overall skeleton, but seems content to remain in the background, quietly exerting gravity. Dark energy stretches the whole scene, changing the rhythm of how structures grow. The Hubble constant encapsulates that rhythm at a particular moment. When different methods disagree about its value, they are really disagreeing about the detailed interplay between all three components over time. You can ask a very practical question at this point. Why should any of this matter to a creature living on a small planet around an ordinary star? The answer unfolds in layers. If dark energy behaved differently in the past, the age of the universe for a given expansion rate changes. So does the time available for galaxies to form and for heavy elements to build up. If dark matter clumps differently, the distribution of galaxies and the environments in which stars and planets form shift. Even small changes in the cosmic blueprint could alter how common certain kinds of galaxies are, how often quiet stars like the Sun appear, and how many stable habitable zones emerge. That does not mean a new cosmological model will suddenly declare life impossible or inevitable. It does mean that every refinement in our understanding of dark components and expansion history feeds back into the question of how typical our conditions are. Are we living in a universe where planets like Earth are expected outcomes in many places, or in one where a long chain of unlikely steps had to stack just right? Webb, by tightening the screws on cosmological parameters and exposing their tensions, is indirectly tightening the constraints on that question as well. There is also a psychological dimension to this. For much of human history, we assumed we lived at the centre of everything. Then we learned that Earth orbits the Sun, that the Sun is one star among many, that our galaxy is one of billions. Each step moved us outward and seemed to make us smaller. Now, in a curious twist, the more we learn, the more special our particular circumstances begin to look. Not unique in any mystical sense, but finely balanced. A calm star in a relatively quiet region of a galaxy that has had time to enrich itself but has not yet quenched. A planet at just the right distance with a stubborn atmosphere. A cosmos whose numbers fall in ranges that allow long-lived structures to exist at all. As Webb helps turn the Hubble tension from a vague annoyance into a sharp scientific problem, it is nudging us to reconsider our place in that cosmos. Maybe our theories are off in ways that will make life-friendly conditions turn out to be more common than we think. Maybe the corrections will go the other way and show that we have been underestimating how rare certain combinations of factors really are. Either way, the stakes of these abstract-sounding constants become more personal when you tie them back to the existence of observers who can measure them. For now, we are in the uncomfortable but fertile position of knowing that our best model of the universe is both deeply successful and slightly wrong. The discrepancies are not large enough to throw everything away, but they are persistent enough that we cannot ignore them. Webb stands as one of the main witnesses in this situation. It confirms local expansion rates, maps distant structures, and counts faint objects, each time implying that some piece of the puzzle has yet to click into place. If you let your mind follow that implication, it naturally drifts back from numbers and parameters to the concrete question that started so much of this exploration. In a universe dominated by dark components we cannot see, shaped by violent events we are only beginning to understand, and governed by laws that may be more flexible than we thought, what does it really mean for a planet like ours to exist? How often do the right conditions line up? How many lonely lights like Earth are scattered across the vastness that Webb is revealing? And how many galaxies race through their brief windows of habitability without ever assembling a world that looks up and wonders? Stand outside on a clear night and let your eyes adapt. Almost every point of light you see is a star inside our own galaxy. And you know now that around many of those stars, there are planets. Some are scorched bare, some frozen solid, some wrapped in atmospheres that would crush you or dissolve you. A few may sit at just the right distance, with just the right air. From where you stand, they are all the same tiny pinpricks, and it is tempting to imagine that worlds like ours must be everywhere. The deeper we look with telescopes like Webb, the more that easy comfort begins to fray. Think back to the red dwarf systems we talked about, the ones that once looked like perfect cradles for life. TRAPPIST-1, with its 7 Earth-sized planets packed close to a tiny, cool star. For a while, it was almost a shorthand for an inhabited universe, a compact necklace of possible water worlds. Webb's measurements cut through that hope with the steady patience of data. At least some of those planets appear to have lost almost all of their air, roasted and stripped by flares from the very star that gives them warmth. Barnard's star tells a similar story in a quieter voice. It is one of our nearest neighbours, a small red dwarf that glows too faintly to see without a telescope. For years, hints of a cold super-Earth in orbit around it stirred excitement. A big, rocky planet in a nearby system is exactly the kind of place you might want to study with future observatories. But as measurements improved, the signal faded.
What looked like a planet may have been a wobble in the data, a ghost conjured by noise. The universe does not always reward our eagerness to find another Earth. Even when the planets are real, their environments can be harsh. Many red dwarfs spin quickly and have powerful magnetic fields. They flare, sending bursts of radiation into space. A planet sitting close enough to be warm might find itself in a constant storm. Its sky could glow with auroras as particles batter its atmosphere. Over long stretches of time, that atmosphere might thin and vanish, leaving behind a world that on paper sits in the habitable zone, but in practice is a frozen or baked rock. The simple diagram with a green band around each star starts to look like a rough sketch rather than a promise.
It would be comforting if this brutality were confined to small stars, leaving quieter regions around Sun-like stars untouched. Webb suggests that is not the case. Around some larger stars, we see super-Earths and mini-Neptunes that migrated inward, dragging icy material with them and mixing their systems into new shapes. Others show signs of past violence in the form of hot Jupiters that skim their stellar surfaces and likely scattered or swallowed smaller planets along the way. Stability is not a given, even in familiar-looking systems. It is something that must be earned through long stretches of relative calm. Our own solar system feels different, precisely because it has enjoyed that calm for so long. The inner rocky planets orbit in near circles. The Sun spins slowly. Major impacts and migrations happened early and then subsided. Water arrived and stayed. An atmosphere built up and persisted. It is natural to fit that story into your sense of normal. Webb, by showing you a gallery of chaotic alternatives, gently suggests that perhaps we are not the rule. Perhaps we are the improbable outcome of 1,000 coin flips that just happened to land the way they did. The sense of rarity deepens when you look at worlds we can actually see directly. Webb and other instruments have imaged a handful of giant planets around nearby stars. Many of them are young and hot, glowing in infrared as they shed the heat of their formation. They sit far from their stars, taking long, cold orbits that may last longer than recorded human history. One such world, Epsilon Indi b, is a brown dwarf-like companion in a nearby system, a frigid Jupiter-like object that shines only faintly. Its atmosphere is full of methane and water vapour, its clouds shaped by chemistry in a realm where starlight is weak. If Epsilon Indi b or something like it has moons, those moons sit in an environment that feels oddly familiar and utterly alien at the same time. They might be warmed not just by the distant star, but by the planet's own residual heat and by tidal flexing as they orbit. Beneath thick shells of ice, oceans could exist for billions of years. No sunrise, no sunset, only a dim sky with a pale star and a large banded giant filling much of it. Yet energy would flow, chemistry would churn.
In that setting, life might not be an impossibility, only a very different story. The icy moons in our own system show how robust that kind of story could be. Europa, Enceladus, and other small worlds around Jupiter and Saturn have global oceans under their crusts, warmed from within rather than from sunlight. Geysers vent water into space. Organic molecules ride those plumes. If similar moons exist around cold giants in other systems, or even around rogue planets drifting between stars, the number of hidden ocean worlds could be enormous. They are not Earth twins. They will never have blue skies and green continents, but they remind you that surface habitability is only one way for matter to organise itself into something interesting. That realisation cuts both ways.
On one hand, it broadens the search, inviting you to imagine life under ice, in deep atmospheres, or around dim embers. On the other hand, it makes temperate, surface ocean planets like ours feel even more like narrow windows in parameter space. You need a star that is calm but not too small, a planet of the right mass, an atmosphere that forms and stays, protection from constant bombardment, and enough heavy elements to build continents and complex chemistry. Each of those requirements is shaped by the galactic and cosmological history we have been tracing. Each one can fail in a dozen different ways. There is another uncomfortable thought. Even if the universe assembles a planet like Earth, there is no guarantee that its stable window lasts very long on cosmic timescales.
Stars brighten as they age. Orbits can be perturbed by encounters with passing stars, wandering black holes, or changes in the mass distribution of a galaxy. Nearby supernovae and gamma-ray bursts can strip atmospheres or hammer biospheres with radiation. Over billions of years, any given temperate world is playing a slow game of chance with many possible exits. Our Sun happens to live in a relatively quiet region of the Milky Way, far from the crowded core where supernovae and close passages are more common. The galaxy itself is not in the middle of a major merger right now. We are between large waves of star formation and collapse. For the entire history of life on Earth, that calm has held. If you see that as a random draw, it makes us feel lucky.
If you see it as a filter that any intelligent species must pass, it makes us feel less alone, because any observers, anywhere, will probably also be in similar rare pockets of quiet. Either way, the conditions that allow you to look up and ask these questions are not trivial. The story does not end with the present. Far ahead, the Milky Way and Andromeda are on course to collide. We talked about what that merger will do to stars and gas, how it can either trigger new bursts of star formation or quench them by heating and expelling fuel. When that encounter plays out a few billion years from now, the Sun will also be entering its own late middle age. It will be brighter. Earth's climate will be under strain, even without galactic fireworks. Whether any descendants of our biosphere are still around to watch the sky twist into new shapes is an open question. Look even farther, and the universe becomes a quieter place. Star formation will slow as gas is used up or locked away. Long-lived red dwarfs will dominate the stellar population. Many galaxies will quench and fade. Black holes will merge and grow, then slowly evaporate over unimaginable times. Dark energy will continue to stretch space, pushing distant galaxies beyond our horizon so that their light can never reach us. In that far future, any remaining civilizations will see a much smaller, lonelier cosmos. Their view of what is normal will be very different from ours. Seen against that timeline, we live in a strangely privileged era. Enough time has passed since the Big Bang for heavy elements to accumulate and for complex structures to form. The universe has not yet stretched so much that distant galaxies vanish from view. Telescopes like Webb can still see back to the epoch when the first galaxies lit up. We can read the story from nearly the beginning to now. There is a sense in which the cosmos is briefly transparent to its own history, and we are alive during that brief window. You might ask whether that is a coincidence or something deeper. Perhaps it is pure chance that one species of primate on one planet evolved intelligence at a time when the sky still carries so much information. Perhaps there is some selection effect, where observers are most likely to exist during epochs when conditions support both life and curiosity. Either way, the fact remains. You are here in a universe that is just old enough to be interesting and just young enough to be readable. Webb's images and spectra are part of that readability. They show you galaxies forming and merging, black holes feeding, stars dying, planets stripping and rebuilding their atmospheres, rogue worlds drifting in the dark. They let you see that the same laws of physics operate everywhere from the core of a supernova to the ice of a distant moon. They also make it impossible to pretend that the universe is designed around our comfort. Harsh radiation, gravitational violence, and vast stretches of emptiness are the default. The gentle pocket we inhabit is the exception. And yet, within that exception, an extraordinary amount has happened. Simple chemistry on a young Earth gave way to self-replicating molecules, then to cells, then to multicellular organisms, then to nervous systems capable of modelling the world, then to brains that can build instruments to study galaxies 13 billion light-years away. The atoms in your body have travelled through stars and explosions and cold clouds to arrive at this moment, where you can sit in a dark room and watch data from a distant space telescope slide across a screen. When you hold all of that in your mind at once, the question of how rare we are begins to shift. It is not only about counting how many planets sit in habitable zones, or how many galaxies host calm, long-lived stars. It is about how many times the universe takes all of that raw material and stacks it in the right order, long enough for awareness to flicker into existence. Some of those flickers might have come and gone billions of years before Earth formed. Others may arise billions of years after our planet is gone. Most will never know about each other. Webb will not answer that question directly. It cannot see life crawling on distant shores or thinking under alien skies. What it can do is sketch the boundaries of the possible. It can tell you how often stars are calm or violent, how quickly heavy elements build up, How many planets keep their air? How many worlds may hide oceans under ice? It can reveal whether galaxies like ours are common or rare at different times. Each of those answers tightens the frame around the great unknown without closing it. In the end, you are left with a picture that is both humbling and strangely intimate. The universe is vast, old, and mostly dark. Its structure is shaped by components we still do not fully understand. Its early years were more intense and more efficient at building complexity than we expected. Its present is threaded with galaxies that live and die in ways both familiar and alien. Somewhere in all of that, on a small rocky planet around an ordinary star, a species arose that can build a telescope like James Webb and aim it back at the beginning. Whether that makes us a statistical inevitability or a cosmic accident is a question that may never have a clean numerical answer. But that uncertainty is part of the beauty. It means that when you look at Webb's images of distant galaxies and faint planets, you are not just collecting data. You are participating in the universe becoming aware of itself. You are one of the lonely lights, briefly illuminating a corner of space-time, asking how many others might be out there doing the same.